Welcome to the company EMAG and to our webinar on the way to green manufacturing, how EMAG supports you in achieving your climate protection goals. Over the next 45 minutes, we want to go into what green manufacturing means, what the path to it looks like for us and maybe for you as well, and what we do on our machines to fit into this path. You have the possibility today to ask us questions in the chat, and we will try to answer them to our best knowledge. My name is Konrad Heimbach, and I'm working for EMAG for 11 years. I started as a developer in the field of fluid technology, which means hydraulic, compressed air, and cooling of machines. And since here is often the biggest problem when it comes to energy consumption, I very quickly had to the topics on my mind to do something better here. We will see a few times later that it is exactly in these areas where the greatest potential still exists. However, we don't want to focus only on this today, but we will try to give a larger picture of the whole energy efficiency for production. And my colleague Uwe is also here today. Thank you, Uwe. Nice that you're here today with me.
Thank you, Konrad, for your personal presentation. My name is Uwe Lachenwitzer. I work at EMAG in Saalach and there in the Central Department for Energy and Environmental Management with a focus on sustainability.
Okay. Today we are mainly talking about machine tools, and where we know best about is turning machines. And therefore, and to warm us up, I have a comparison of things that we probably all can classify from our daily life together with machines. So here I have a family home, a very modern home that is already using heat pumps for hot water and heating. And then we have two machines. One is slightly the lower end when it comes to energy consumption, and one is a little bit larger machine. And then we have two passenger cars here as well. One is an electric car and the other one is a gasoline engine. Now, such different things are not easy to compare at first because they use different types of energy like electricity or gasoline. So in order to find a common unit, let's look at the CO2 emissions generated by each. So while you can easily see those emissions coming out from combustion engines when you take a look at the exhaust, it is not so easy to see for the electric things because they don't produce emissions themselves. But of course, there are also emissions caused, but they occur previously during the production of the electricity. So in order to take this into account, there is a CO2 emission factor, which is recalculated annually and which indicates the average CO2 emissions per kilowatt hour that was generated during the production of the electricity. In 2020, this value was 366 grams per kilowatt hour for Germany. And we could also see that factor falling annually over many years, which is mainly because of renewable energy sources, but it also rises again in 2021. By using those CO2 emissions, we get a good comparability of these different things. And the comparative values are shown here in two diagrams, blue diagrams here and here. And what we can see is that such a car causes quite large emissions, both for the combustion engine and also for the electric car. But fortunately, we are not driving these cars around the clock, but this is often the case when it comes to your house or also for the machine tools. So that's why we have in the lower parts the emission values per year based on typical operating modes, which is 2-shift operating for the machines and 20,000 kilometers per year for the cars. So viewing over the year, the picture switches completely. And this concerns not only CO2 emissions, but also the cost for electricity or also gasoline. What we can see here is that the amount of emissions caused by a machine can quickly times 2 to 8 compared to a car or a house. So that's why we have to do something. That's why we have to reduce this consumption in production. And we have a few topics here for you today, how we can do that. Let us start with taking a look at the agenda for today. We will start with the topic of climate neutrality, including the legal situation, which Uwe will present a little bit about. Yeah. Then we will continue with the energy efficiency in mechanical engineering, and we will look at this from 4 sides. From the side of the manufacturing process, from machine concepts, from components we use inside the machine, and from side of energy management inside the machine. We also want to shed a light on what we can do with the large amount of stock machines existing. So the keyword here is energy efficiency retrofits. And then we have something like the ETA factory, into which we want to give a little insight. We will end the topic with monitoring of energy data. So let's first of all take a look at climate neutrality. Uwe.
Thank you, Konrad, for your short introduction. In my presentation, I will give you a brief insight into climate neutrality and why it is becoming so important for us. First, I would like to show you the meaning of climate neutrality in more detail. The term carbon dioxide in this context stands for carbon dioxide, as well as other greenhouse gases such as nitrous oxide or methane. The latter are converted into so-called carbon dioxide equivalents. Climate neutrality means that there is a balance between carbon dioxide emissions and their absorption from the atmosphere. The absorption of carbon dioxide takes place in so-called sinks, for example, through the growth of trees and moors. A company is considered climate neutral if its processes, products and services do not further increase carbon dioxide in this atmosphere. For example, the avoidance of greenhouse gas emissions can be done by reducing, avoiding and offsetting. The following legal requirements regarding greenhouse gas reduction currently exist as follows. In the global area, Paris Climate Agreement of 2015, the goal to limit global warming to well below 2 degrees Celsius, better 1.5 degrees Celsius in this century. In Europe, European Green Deal of the European Commission's reduction targets for 2030 minus 55% compared to 1990, and climate neutrality by 2050 in Europe. In Germany, the Climate Protection Plan 2050 with 2 reduction goals, target for 2030 minus 55% compared to 1990, and reduction target by 2040 minus 85% compared to 1990, and the climate neutrality in Germany by 2045. The state of Baden-Württemberg received its climate protection law in October 2021. The reduction target for 2030 minus 65% compared to 1990, and the climate neutrality by 2040. In Germany, there are tools for implementation, for example, the carbon dioxide pricing.
Well, we already have the first question in our chat. You were talking a little bit about subsidies, and this question fits very well, I think. Are there government funding programs for the industry as well?
I think in Germany there are a lot of government requirements. For example, the BAFA program with the Module 4. And the Module 4 is the energy and process optimization for a plant and processes.
Okay, so at least for Germany, this can be used to promote energy efficiency measures in production. Maybe, I think we don't know exactly, but there are other programs as well in the rest of the world.
Mm-hmm. I now come to the next point. What is the significance of climate neutrality for companies and why are we doing this? First, general requirement of the federal government to implement the climate protection plan, climate neutrality by 2045. Evaluation of the topic sustainability is included in the customer scorecards. Carbon dioxide reduction is part of the sustainability. Active request by customers to enter environmental relevant information, data and projects in databases such as EcoVadis or CDP. Improvement of the company image and obtaining grants and cheap loans from credit institutions. In Germany, at the moment, cost increase, for example, increase in carbon dioxide price step by step to 55% per ton by 2045. For example, diesel, petrol, heating, oil and natural gas are increasing. And why on the budget search for compensation increase in resources and energy efficiency are necessary. And the last one, long-term existence and success assurance.
Well, we already have another question here. I think it fits in very good. From which company size are these sustainability reports mandatory?
It's a good question. The following criteria have been defined. More than 250 employees and turnover over more than 40 million euros and balance sheet total of, I think, 20 million euros. And at least 2 criteria must be met by your company.
Okay, so that we at EMAG have to do it for sure, and probably it's also affecting some or most of our customers.
Yes, the start of the business year 2055.
Okay.
Next, let's take a brief look at the international recognized standard of the Greenhouse Gas Protocol. There, the activities of companies are divided into the 3 main categories, so-called scopes. Scope 1, direct emissions, for example, heating, and Scope 2, indirect emissions, for example, processed electricity, which are mandatory under the Greenhouse Gas Protocol. Scope 3 is divided into upstream and downstream emissions, and it's currently except, for example, it can only be applied in part. The improvement of the emissions balance is achieved on the one hand through energy optimization or carbon dioxide compensation. And the goal, avoidance of emissions within the scopes 1 to 3 and the zero net emissions in the company and in all processes along the value chain. Here you can see an overview about the greenhouse gas emissions for scope 1 till 3. In the middle, the scope 1 with the heating and the process emissions, for example. Scope 3, upstream business travel, transport, delivery, and scope 3, downstream transport and delivery. I now come to my last point, climate neutrality, unequal climate neutrality. Climate neutrality today is made up as follows. First, compensation. The next one is renewable energies, energy efficiency, and the last one, energy flexibility. The balance sheet climate neutrality takes place in the short term. The future compensation of climate neutrality based on the following assumptions. First, the renewable efficiency, renewable energies, energy flexibility, and the last one is then the compensation. Climate neutrality through emission reduction in the long term.
Well, another question we have, very good question. I think, what is the EMAG group doing to protect the climate?
Okay, thank you for the question. At the moment, we are currently creating a carbon dioxide footprint for each EMAG site. We will then define and implement specific carbon dioxide neutrality targets. And many EMAG sites are already supplied with renewable energies today.
Okay, that means we are in the middle of the process, but there's still some steps to go here for us as well.
Yes.
Right.
To put it simply, my conclusion is this: if you know your emissions and where they occur in the value chain, you also know where they can be reduced. Thank you very much for listening, and Konrad will now follow with his presentation.
Uwe, I would like to take up the picture you gave with the scope 1, 2, 3 divisions again and try to apply it to a turning machine. In an ideal world, we can expect on such a machine raw parts going in and finished parts coming out. But as we all know, we don't live in such an ideal world. There's many things more we need to have that process running. So, first of all, a machine needs electricity to run. Then there's usually also a connection to compressed air, which in turn is generated from electricity most of the time in-house or in the factory itself. And then we have operating media as well, like hydraulic oils, lubricants, coolant, filters, and so on. And on the other hand, there's not only finished parts coming out of the machine, but maybe also rejected parts or scrap parts. This is obviously never happening if you're using an EMAG machine, but it could be in some other cases. Then we have consumed operating media caused by oil changes, filter changes, or coolant changes. And then at the end, we also have waste heat emitted by the machine into the factory, or sometimes even into a water network. If we take a look at this, the electricity only is a scope 2 emission. Everything else here is scope 3. Scope 1 usually doesn't exist on a turning machine unless there's maybe a defect in an air conditioning unit where the refrigerant can escape directly. But again, of course, this never happens if you're using EMAG machines. So on other machines in production, this can look different. For example, if you have a hardening furnace, it is very obvious to see when it has an exhaust flare, where the exhausts are burned, that these machines cause scope 1 emissions themselves. So, but what does that mean for climate neutrality, or how can we get better here? So first of all, we have to make sure that we consume less electricity. This reduces directly our scope 2 emissions. Then we also want to consume less compressed air, which is also scope 2 if you generate it from electricity in your factory. Of course, we don't want to have scrap or reject parts. And then another thing that also pays into climate neutrality is using less operating fluids on the machine, or using environmental friendly fluids. For example, if you only have to change 10 liters of oil instead of 40 liters when you're doing an oil change, this would be better. Or maybe you don't even have to do an oil change because the machine is working without hydraulics at all. In the end, it is also about avoiding waste heat or utilize it to do something sensible with it. The ETA factory will give us a little insight what is possible here. In the end, everything that increases productivity helps us to reach better climate targets, because usually you have more output in less time, which means you can have the machine run one shift less and save energy. So from the big picture of climate neutrality, we now dive into energy efficiency. We will divide this topic into 6 areas. I will go briefly over these 6 areas and then followed by more detailed examples afterwards. First of all, we want to start our production with looking at the manufacturing techniques itself. The manufacturing technique or the process of a workpiece has by far the greatest influence on the energy efficiency with which a component is produced. So one example is you can cast a product or you can mill it from a block. Or you can do machining by turning or grinding. The energy input in each case is obviously different. But in order to exploit this potential, it is often necessary to start from scratch, because material and raw parts have an influence on what is possible in the end. Once the production process has been defined, the next step is to find a suitable machining concept. Easy automation plays a bigger role here because it saves energy for handling processes and also can increase productivity. Another thing we want to take a look at here is multi-technology machining or duo machines. When the machine is fixed, we can do further optimization on the components internally, which means using efficient engines or efficient control strategies or reducing compressed air. Fourth point here is the energy management inside the machine. It is a matter of how do we handle the energy needed inside the machine, like reacting to waiting times and so on. And then the fifth point here is AI-based optimization. That's all about how we use data from the machine to increase process or quality on one hand, which means produce less scrap parts, provide the possibility to do targeted maintenance and reach an overall higher availability of the machine. But this data can also be used directly to save energy. We have an example of using it for temperature compensation later on. And then last but not least, we have the data-driven production planning here, which can be seen superior to the machine. And here it is about optimizing production sequences, which in the end will reduce cycle times and then hopefully lead to a machine that can be switched off earlier. We can see overall not only efficient components are affecting our energy efficiency, it is much more that we have to pay attention in terms of efficiency. Let's start here with energy efficient manufacturing processes and an example from our own production. We can very good show here the differences of different manufacturing processes. What I brought here is a machine base, how we use it normally in every type of machine. So classically, machine bases are made from steel casting, and for this purpose, steel is melted at high temperatures and with a large amount of energy needed, and it is poured into a mold. An alternative to using steel casting is creating machine bases out of mineralite. Mineralite is also a casting, and you can imagine it like when concrete is casted. So that means it is casted at cold or room temperature. And here we are not talking about energy savings of 5 to 10%, but a full 75% of energy savings. So we can see very well here that the manufacturing process can make an enormous difference, and the efficiency gains we get are much higher than if we start the optimization later in the process. So as a conclusion, consistent energy efficiency starts by the very beginning with the selection of the best manufacturing process. And I also have an example for metal cutting here. Often when you invest in a new machine, you probably already have the workpiece in mind that you want to manufacture on this machine. And if you have the chance to start on a greenfield, we also start here with looking for the best manufacturing process. The example I brought here is a comparison between grinding, hard turning, and power skiving. I have to say that components that conventionally are manufactured by grinding can often be also produced on a turning machine by using one of these techniques. And they can also achieve requirements that you usually only associate with a grinding process, like being twist-free or having very good or high surface quality. A grinding machine usually has a high energy requirement because of the grinding spindles, because of sealing air they need, and probably oil-air lubrication systems, and also complex coolant systems, sometimes even with temperature management, which all cause a lot of energy consumption. A turning machine has an advantage in terms of the energy. The data we see here was recorded on a test where we machined the same component on a grinding and a turning machine by using these technologies. And we can see that the saving potentials of power skiving compared to grinding in this case is over 90%. What we can learn here is that we have to ask the question which manufacturing process is the best or is the most efficient to produce a component. And it is not always the obvious solution. And we as EMAG has not only the know-how to build machines, but also for a lot of different manufacturing processes. And we will be happy to find the most suitable solution for your process as well. So once the manufacturing process has been defined, the next step is to find the best machining concept for this process. And here automation plays a major role. A lot of workpiece handling between the machines requires additional energy, and machines that are suitable for serious production without needing extensive automation pay into the efficiency. We can reach this, for example, by integrating part storages or giving a simple manual loading and unloading capability. Another concept aims to reduce the non-productive time by loading and unloading in parallel with the machining process. We call that pendulum machining. The saving of energy here is by increasing the productivity and reducing the non-productive time. And then we also have duo machines. Basically, these are two machines that share one set of peripherals like hydraulic, cooling, or even the control system. If this concept fits, a duo machine has an advantage regarding energy consumption compared to two single machines. And last but not least, we have the multi-technology machining concepts here. Here, several machining technologies are combined on one machine. This is especially an advantage because we can reach high quality with only one clamping. But on the other hand, we have much less workpiece handling, and we also have the benefits, like on the dual machine, that we are using one set of auxiliary units. So what we learn here is that the suitable machining concept reduces workpiece handling effort, and that also specialized machines can be an advantage over universal solutions, also when it comes to energy efficiency. After selecting the manufacturing process, the machining concept, it is then important to take a look at the energy consumption inside the machine and improve it. And therefore, we often create such an energy flow diagram. We can see here which component uses which electric power. We get a very similar picture, no matter if it's a small machine, a big machine. So large proportions of the energy are used in auxiliary units like cooling, hydraulics, or coolant, while only 1/3 of the total energy requirement goes to the drive system. Interesting here is also that the difference between air cutting and the actual cutting is only about 10%. So that means 10% of the total energy invested goes to the chips, and 90% are waste. Of course, we still need this 90% rest to get the machine doing its job. But when it comes to major improvements, it makes sense to look at them first, as they are the biggest energy consumers. And also, there is usually a lot of room for improvements without affecting the machine abilities. Such an energy flow diagram is also the first thing we do when we take a look for revising existing machines. Because on this base, the potentials for increasing efficiency can be identified very good. An overview of these potentials can be seen here. Our machines at EMAG are constantly being further developed, also with regards to the energy consumption. That means the things listed here are our state-of-the-art on a current machine today, but for many existing machines, these are potentials that can be quite interesting and can usually also be implemented there.
Konrad, we have a new question. Are EMAG machines out of the gate energy efficient?
Yeah, good question. Of course they are. But I try to answer that a little bit more in detail. And I try to answer it from the perspective of the machine itself, because we already heard also the process and the machining concept itself has a big impact. But let's take a look at the machine inside. The things we see here, I said, are standard in our machines. And we have a fixed cycle of releases for machines. And in this process, new innovations are regularly transferred to every machine type. So that means if there is a newer, efficient solution, we roll out this to every machine regularly. And so over the years, for example, we have optimized our hydraulic systems by using demand-controlled pressure providing, and also lightweight design plays a bigger role. That means reducing the masses that are moving for the tail slide, for example, and we also use FEM methods here to ensure that there's no compromise regarding dynamic behavior here. In many machines, optimizing the lightweight design also means we can get rid of hydraulic counterbalance systems. I think that answered it. Yeah, I have just mentioned that these measures can also make sense for existing machines. And we all know that we have rising energy prices. Uwe told us about EU regulations, the Green Deal, that we target greenhouse neutrality. And this all makes energy efficiency also very interesting for old machines. I brought an example here of a shaft turning machines, VTC 250, with the year of construction in 2008. First of all, we created an energy flow diagram similar to the one I was just showing, and we identified directly on the machine if there's wear or poor adjustments that are affecting energy efficiency. Things we always take into account here is, do we have leaking on clamping cylinders, do we have air leakage, or other settings for compressed air correct. In this case, the machine was in top condition and very well maintained by the customer also. But anyway, we identified 3 measures where the machine was no longer state-of-the-art or where the customer already upgraded his infrastructure. But the machine was not using it yet. And so we implemented 3 things, optimizations for the hydraulic unit, for the coolant pump, and also for the cooling unit of the machine. This led us to energy savings of more than 18,000 kilowatt hours per year, or 6.7 tons of CO2. If you remember our family home on one of the first slides, this is more than twice the energy needed for a family house. Very interesting here is that the rework for this was done directly in the production of the customer and took us 1.5 days. That means after 1.5 days, this machine could directly go back into production. If we take a look at the payback period, if you use subsidies, we also heard of Module 4 in Germany. If you use that subsidies, the payback period will be 2.5 years about. If you not use it, it will be 3.5 years. The customer here predicted that he wants to use the machine for over 8 years. So that means in the end that it's not only worthwhile for the CO2 balance sheets, but also financially in the end. What does it mean for you? We at EMAG, we have to know how to make even our old machines fit again, and we are also very happy to do this together with you. Just get in touch. So now we jump from the retrofits into the future. EMAG is a partner of the ETA-Fabrik, or ETA Factory, which is a research project of the University of Darmstadt, together with several partners from industry, construction, and technical building equipment. It is sponsored by the Bundesministerium für Wirtschaft und Klimaschutz in Germany. This picture here shows a demonstration process chain for the production of a pump component. We have a hardening furnace on the left side, and then we have a part cleaning machine, a turning machine, and a grinding machine. Research inside the ETA Fabrik is done for efficiency optimizations of individual components inside the machines, but also utilizing synergies in this production chain. Like the waste heat from the turning machine is used to heat up the cleaning machine. And also deeper integration of this production in its whole surrounding, for example, by using the waste heat of the furnace to generate electricity, or to heat up water, or do heating for offices. The ETA Factory is a building that actually exists on the campus of the University of Darmstadt. And on one hand, research continues here, but interesting also is that there are workshops and training courses for industrial companies provided. If you want to experience energy efficiency taken to a maximum level in the production, this is the place for you to go. one actual topic inside the ACTA factory which we are following is the project of temperature compensation. Temperature compensation of pause and cold start behavior on the machine. You probably also do it like this in your production, that the machines are switched on before the production starts, and then they are warm up first. And during the breaks, the machine switches to warm holding processes. This means similar to the air cut I mentioned before when we were talking about the energy flow diagram, 90% of energy invested compared to actual production, but we absolutely have no output. This means a maximum waste of energy here, but it is still maybe better than starting with scrap parts into the production. For us, it is exactly where we are attacking with this project. The goal is to make warm-up and warm-keeping processes unnecessary by compensating this behavior. And for this, we are working together with Anicision, which is a company focused on using data and AI in production. For this purpose, there are several measuring points inside the machine, which we feed together with the time history, which is very important in this case. We feed it to machine learning models, and we get back compensation values for each axle. This topic is a small insight into the current research we're doing within the ETA factory. My last topic for today is about energy in the machine as well. And it is all about making energy consumption visible and emissions transparent. Therefore, we developed the energy monitor. Electricity and compressed air are the two media usually connected to every machine, and those two media are recorded in a similar way than an electricity meter in our house. But by integrating it inside the machine, we get several more interesting possibilities. A big advantage is that we get a reference to machine conditions or to the workpiece. And this leads us to building characteristic values like energy demand per shift, or energy requirement per workpiece, or even energy consumption in unproductive time, while the machine is in waiting for workpieces or doing warm-up processes. And with making this transparent, you might get into thinking, is this really necessary, and what can we do to minimize it? We also visualize the CO2 footprint here. And we also can lower that down to CO2 emissions per workpiece produced. If there are any deviations from optimal consumptions, this is made visible by indicators on this dashboard. For example, a higher energy consumption than usual in the current shift is indicated with a red ring. If you have already experience with our IoT solutions, you probably recognize that this energy monitor fits in here, and that means it can be called up directly on the machine. It can be seen centrally on a production dashboard, or you can also access this from your workplace. In the future, the development will continue here by using this energy data also for condition monitoring, which means we can use energy data to detect increasing leakages from compressed air or caused by worn-out cylinders at a very early stage, and then we can inform the user. Yeah, let me sum it up what we just heard about. First, climate neutrality is not just a trend, but a must. The biggest lever for energy efficiency in production is the manufacturing process itself. And then we have energy efficiency that also pays off financially and also makes a lot of sense on existing machines. In the end, it doesn't end with the efficient machine, it is also important to avoid waste during the operation, and also monitoring can help with this. Yeah, at this point, we still have time to answer your questions, and we will see if there's something already come in.
I think it's for you, Konrad. We have old EMAG machines. What is the process and the duration of optimization?
Okay, yeah, maybe first of all get in contact with your contact person at EMAG or to our EMAG service. Already providing which machine could be in focus here, and then we can check based on the documentation we have available what measures make sense, and yeah, we will give you we will work out these measures and talk together with you about those things. I think until you get an answer here, this is maybe 1 or 2 weeks. Important, maybe let me say one more thing here, because this is asked often. If you want to claim subsidies here, you must involve an energy consultant already before you get the first quote from us. So this is very important here.
Next question, I think it's for you too. Does the energy optimization of the machines take place at all locations of the EMAG group, for example, China or India?
Yes, we make absolutely no difference here. We have a centralized development at EMAG, which also means that every solution, every efficient solution goes into every machine type, no matter where in the world they are built.
I think it's no question.
Okay, no more questions? Good. Then thank you for joining us today. Have a great afternoon and great rest of the week.
Bye.
Bye-bye.